So I said I'd send you an example from 8.6. I'll send you two actually. Example 1 and example 2. Example 1 will be to find a power series that represents the function x over 3 plus 4x squared. So we're going to try to do that. We have two major ways that we try to find these, by which I mean two ways we write it down. One is chains, by which I mean a chain of equalities. These aren't technical terms, this is just to describe it. The second way is with a pair of columns. You can always use whichever one you prefer. So we're going to do a chain because we'll probably do that more often. And starting with our chain, we start with what we have. I know that I have x over 3 plus 4x squared. And that reminds me a little bit of the geometric series. 1 over 1 minus x, which equals the series x to the n from n equals 0 to infinity. So I want to make it look like this. And in this series, like we said in class, the 1 and the 1 and the minus are all important. So I want to factor out until I have those terms. So I'm going to factor first, factor, which gives me an x over 3. I'm factoring out the 3, so I end up with a 1. When I factor the x from the top, I'm left with a 1. When I factor the 3 from the bottom, I'm left with 1 plus 4/3 x squared. Now that's not too bad. I now have a term in front that I can still distribute through my power series, and I've got a 1 over 1, but I need to change my plus to a minus, so I'm going to do that. This is x over 3 times the function 1 over 1 minus negative 4/3 x squared. We don't really care how ugly this term on the right is because it's going to be substituted. So the right side looks exactly like our geometric form, so I can say that this equals the series, x over 3, that still hangs around a little bit annoying, times the series from n equals 0 to infinity of our ratio, negative 4 over 3x squared raised to the n. We want to make it look nicer. If you remember, most power series look like the series c sub n times x to the n. So we've got our coefficients in front. We want to get that here. So this is x over 3 times the series from n equals 0 to infinity. We'll pull our negative 1 out even more separately because it shows us immediately we're alternating. We've got our 4 to the n, we've got our x to the 2n, and on the denominator we have a 3 to the n. We're almost done. Notice our power series doesn't have anything in front of it. So we want to bring our x over 3 inside the function, just by multiplying. So that equals the series from n equals 0 to infinity of negative 1 to the n, 4 to the n, x to the 2n times x, which is x to the 2n plus 1. When you multiply things with the same base, you add their exponents, x to the 2n and x to the 1. Same on the denominator. We've got 3 to the n and 3 to the 1, so that's 3 to the n plus 1. And that's it. This is now a power series that represents our original function, x over 3 plus 4x squared. It's centered at 0 because our x isn't subtracting anything. We're curious about the radius of convergence or interval. Well, we used the geometric series, which converges when the absolute value of x is less than 1. We didn't plug in absolute value of x for our ratio. We substituted in. So we're going to have to check when the absolute value of negative 4/3 x squared is less than 1. So we can get rid of the constant pretty easily. That means x squared is less than 3/4. The absolute values went away because x squared is always positive. And to solve this, you're going to have negative square root of 3 over 2 is less than x is less than square root of 3 over 2. If you think of the x squared function, you're asking when is this less than 3/4? It'll be from negative root 3 over 2 to positive root 3 over 2. So that's our interval of convergence. Since the ratio, the geometric series doesn't include the 1, doesn't include the endpoints, we don't include ours either. So our I is going to be negative root 3 over 2 to positive root 3 over 2. Okay, the next example will show you how to use a pair of columns.